is a part of MATLAB, and the good thing is we could simulate dynamic system and using the block diagram. So you find that the major job for you to do is to find the correct block modules and then link them together. So what you need to do is you need to decompose the model into different block modules and then link them together, and just like you playing Lego. I believe you like it. So here I give you a very simple example and show you give you an introduction of Simulink, and then after that, and then I will work with you together to use Simulink to solve two equations ODE model. So this is the homework problem, right? So I will not give you a solution today, but I show you how to solve the problem, right? So this is so we want to control the liquid H. So this is H in the tank, and then this the flow and that flow in the system. The flow rate is Q in. So this valve is closed. So the liquid flow out in through this valve, right? Flow in, flow out, and this is the level transmitters that measures the H value, right? I believe you know. So from the course and the actual handout and in process control, you should get this equation, right? So the dH dt, right? Q in minus kV1 is the kV1 here is the valve coefficient, right? The flow rate already given here, and D is the diameter of the tank, and also here. Then here is the cross section area of the tank, right? So now we want to use Simulink to solve this equation to get the profile of H over time. Right now, I already built the Simulink model for you, and I just want to show you how to link the ODE model with the Simulink and module here. So here you can see the integrator, right? So integrator, and so the output of integrator is H, the input of integrator is dH dt. So this integrator actually is and calculate H, right? dH dt and over dt from 0 to the time t, right? And then based on the initial value, here's it's initial value. So initial value plus the deviation derivative and then the integration of the derivative over time. So this is how this module is doing, right? So you need to set up the initial value in this integrator module, and you just double click of this module, and then you could set up the initial value. Okay, I'll show you later. So here you can see, and this is how we could represent the equation, right? One equation, one ODE, the first equation, and then you should get one integrator. Okay, now we need to calculate dH dt, right? So here the equation. So you could input the equation here. So dH dt equal to Q in minus kV times the square root of H, and then divided by the A is the cross section area. So this is the divided by A, right? This is the, so this one is the Q in minus kV times square root of H, right? So this K in minus kV and times the square root H, and then this term is A. So this is a module for us to divide this term, the K in minus kV times H, and by with a, right? So therefore you can see we decouples the equation into two terms, right, with the division operation, right? Okay, now we need to further calculate a, right? A equal to pi over 4 times the diameter and the square of diameter, right? So therefore here this is the gain of time pi over 4, and this is the square of diameter. So therefore a equal to pi over 4 times and d square, right? So to calculate this square, and then we need to times 2d together, right? This is 1d and this another d, so this is the multiplication module, right? Okay, and in this example we need to change the diameter unit from millimeter to meter. So therefore we need to divide with the times diameter with 0.001, right? So you can see based on this, and we could calculate a, right? So this block show you how to calculate a, right? Okay, now we need to calculate q in minus and kv and times square root h. So similarly, you see we have q in minus, right? So there's two terms here. The first one is q in. The second term is the kv times and square root h, right? So q in, and so this is the q in, right? But we need to, and you can see the time unit here is a minute, right? But we need to change the time from minute to second. So therefore we need to divide q in by 60. So this is how we change the minute into the second. So therefore this is the q in, right? At the same time, we also need to calculate kV times square root h, right? So this is the module. We calculate kV and times square root h. So as you can see, we could decompose these terms into two terms, right? The first one is kV. The second term is the square root h, right? So this is kV, and this is the function for the square root h, right? So this input, this is h is the input, right? This is h, right? So h comes from the output of the integrator. So the h comes from the output of integrator, and then this is the function of square root h. So therefore we could get square root h here. Okay, and then times kV, and then get this term, right? So based on that, we could do the simulation, and at the same time we need to record the time. So this we have the module to record the time, right? And then we change the unit from meter to millimeter, so it times 1000, right? So you could see in this diagram that there are some important module in Simulink, and the source means, for example, this is the source time, the clock time, and here the Q in, and for example the step change in the Q in, right? And at the same time we also so also a constant, and there are a lot of constant parameters here, right? These parameters. Also we also have math operation, right? For example, multiply. See, this is a multiply, this is multiply, and then we also have divide, and also summation and minus, and also we have gain, right? So at the same time we also have the integrator as specific for the differential equation. Okay, differential equation. So one differential equation should have one integrator, and also we need to define some function. For example, the square root of h, or some other complicated. You could define any complicated function. I show you later. It's not changing. Also, there's some, we need to record the data or display the output profile, right? So we have this was sync. sink here, we have, for example, we could display the final value. You can use scope to see the time profile. You also can save the profile into array. So this is a vector, okay. And then we could plot the profile with the time. This is a time vector, right? So this is the module. This are the modules we use for this example. So you can see, compare with the ODE model here, we decompose the ODE model into different terms, and for each term we further decompose them into different module, right? And then we link this module together just like playing Lego, and then you get the simulation. So here I want to show you, hey, you might ask me how we could get this block module. So most of our job to do in the simulation is you need to identify the correct modules. Okay, so now I want to show you. So here, so you could there's a library, and you could click the library. I will show you later how to get the library, right? In the next example. So here's the library. So you can see Simulink. This is the module, and we could get. So for example, you could see the source here, and then you could see step here, right? You also see constant here, right? So also you could see the math operation from the Simulink, and you could see, for example, the product, and then square root, and the right, and the divide, right, and other operations. Also, you could see the integrated block from the continuous here, continuous, and the category. You could see an integrator and derivative. Okay, and then you also can define your own function, as I mentioned. So here's user defined function. You could define your own function. FCN is the function you could define. You could define the function by specify the input and the output. Okay, and then this is the sync block. See, you can see displays display the final value, right? And then you also can save the data into array. Okay, and then you could also use scope to show the profile, right? Now I give you one example and to show you how to solve ODE model using Simulink and step by step. And this is a CSTR model, and so this is a XML reaction, and component A is converted to B, and the CSTR is cooled by the water with the temperature Tc. And here we have the differential equation for Ca for temperature, and the rate constant is changed with temperature following Arrhenius equation. And you can see that Ca and is influenced by the temperature, right? Because the K is here. K is calculated using this equation. So we need to know temperature and to know the K value. And to get the temperature value, we also need to know the Ca value, right? So you can see, and this model is highly coupled, right? And also K and is determined by this nonlinear equation. Okay. Well, MATLAB can solve any complicated nonlinear coupled equations. Now this is just one example. The values of the parameters are shown in this table, and the initial condition is also given. Let me see. I think in the next page. And so in this example, the cooling temperature of the water decreases to from so this is condition here from 300K to 290K. So this first scenario. In the second scenario, TC is increased to 209K. So we need to get the time profile of the temperature for these two scenarios. So this is the problem we need to solve. Okay. So now, before I show you the result and I give you an overview, a big picture of how to represent the ODE model using Simulink. Right, this is the ODE model, and actually I have already developed in Simulink. Right, well, your model maybe can look a little bit different from mine because you can move these blocks and modules around. So you can see for the differential equation of CA, we could get we add the integrator here, right? And then the derivative of CA over time equal to Q over V times CAI minus CA, right? And then minus this term KCA, right? So therefore, you will see I put the equations and under the module so that you could check your equation and also check your model, your Simulink model, and I think this can help you to build a model correctly in a short time. Okay, so you can see we can decompose the derivative of CA over time t by the summation of these two. Actually, the first term minus the second term, right? So for the QV times CAI minus CA, we could further decompose this term by the product of Q over V times CAI and minus CA, right? Okay, and then we could further decompose this term into CAI minus, here's the minus sign, and this is CA. Okay, CA is from here, right? This CA. Okay. So similarly, we could get Q over V using this dividing module here, Q over this V, this Q, right? Okay. So by this way, we could get CA, and so to calculate K times CV, we need to calculate K, right? And this is the module we put the function we use to calculate K, right? And then K, and you could see we have there's three vectors here. Actually, three elements here: U1, U2, and U3. So this U1, and this U2, and this U3, right? And then we can input U1 here, U2 here, and this U3. And U3 is temperature, right? Temperature from here. This the integrator for temperature, right? So by this way, we could get the differential equation for CA. Well, similarly, we could represent the differential equation for temperature, and here, and by the summation of these three terms, right? The first term, this is the first term here, right? And it's Ti minus T and times W over rho times V, and then the second term is here, right? So add them together. See, we add them together. Second term is minus delta T HR times K times CA over rho times C. This third term here, right? U V over rho times V times C, and then times TC minus T. Okay, so and then we could, for each term we could further to decompose them, right? For example, for Ti minus T here, we could, this term can be represented by the product of Ti minus T times W over rho times v. So, and this term equal to ti minus t, right? This t, and then this term equal to and here's w, right? W, and divided by rho times v. Rho times v equal to rho, and this the v, right? This the v here. See this v, you can see v here, all the way down. Okay. So for the second term here, delta HR times K times CA over rho times C. Similarly, we have three terms together, times together. So the first term is CA. So this CA, right? And then the second term is delta minus delta HR times K, and the last term is here is rho times C, right? You can see minus delta HR times K times CA over divided by rho times C, right? CA already, we could get CA from the differential equation for CA, right? And then here's the second term delta HR times K, so we could times K, this K, with this is minus delta HR, right? So this is minus delta HR here. So for rho times C, and you could get this is C, and then so this C, and this is rho, right? This is rho here, you see all the way rho. This is rho. So therefore, you could see we could decompose the equation into several terms, and then we could further to decompose each term into individual modules. Similarly, we could get the decompose the last term here. You can see and this term equal to UV over rho times V times C times TC minus T, right? And then this term equal to U, this will be UA, right? This will be UV, right? UV. So this should be UV, and here is constant. And here this term is the times the product of three elements. Here's the rho times V times C. Okay, and for this one, TC minus T. So this TC is the change. We could have this. We had step change here, right? And then this minus T. This is T, right? This from T. Okay. So I'll now give you a big picture, and then we also record the data, right? The output profile, and using the array, this array, and then we could also using the this scope here, the scope, then we also can display the final value here. Okay,